Okay, hello everybody and welcome back. So yesterday, last lecture we talked about the interior of Earth. So I'll just briefly try to cover a few points and then we'll move ahead and talk about the plate tectonics today. Now yesterday we spoke, we discussed about the different layers, and we also talked about that the Earth is not homogeneous. It has a different composition, as well as the different layers have different compositions. In short, we can say that the Earth is not homogeneous. Okay, so and different layers have different properties, as well as what we see is that the composition is also different. Okay. The most important thing which we were discussing yesterday was that the different discontinuities which exist between different layers, and these discontinuities which we were talking yesterday about the mode discontinuity or the Conrad discontinuities, they are marked with the help of seismic data, and of course the seismic waves which behave differently while traveling through this layers or through the interior of Earth, and their velocity changed and all that. So based on that, they have marked this boundaries. Okay. So the mode discontinuity, what it exists is, again, we can say that this exists between the crust and the mantle. Okay. And the crust, basically, which is a low density, which is composed of silicates rich in aluminum and potassium, and the mantle, which is composed of silicates and with higher density containing magnesium and irons. Okay. So this we discussed. Now if you move further towards the interior of Earth, what we find is that we are having then the mantle, which is comprised of the partially molten layer, which is known as asthenosphere. Okay. Now there is no clear cut discontinuity is been named between the lithosphere and the asthenosphere, or we can say the crust and the part of the asthenosphere. There is no clear cut, but it has been marked that this is a low velocity zone, and this we will discuss or talk when we are talking about or discussing about the interior of Earth later on. So now the another important part here which I would like to emphasize is that the asthenosphere, of course we will be talking with as you move ahead in this lecture, the asthenosphere is responsible for the movement of the tectonic plates on this universe. And then another important part is that the liquid core. Okay. Now this liquid core is responsible for generating the magnetic field, and this is what we call as a geodynamo. Okay. So this is one of the important part, and why this has been termed as a geodynamo, I'll talk in few minutes in next slide. Okay. So moving ahead in this, so here the complete composition of the interior of Earth has been given, which you can refer with, and as we discussed in the previous lectures, that the heavier material or having the higher density segregated at the base, and then we are having the lighter material at the surface. Okay. So that what we see is that the lighter ones are towards the surface, which are forming the crust and all that, whereas the heavier one like nickel and iron are been seen in the core and core part. Okay. So this is again the very much similar, which the sections talks about the density part of the Earth's interior. Okay, right, starting from the crust, including continental and oceanic crust, and then you are having a mantle, core, and entire Earth. Okay, so entire Earth average, if we take, we are having the average density, which is around 5.5 G. Okay, now moving ahead, this is the important part. Now this magnetic field basically is been like if you take an Earth, then it acts as a giant magnetic bar. Okay. Now one very important part which I would like to mention here is that this magnetic field, okay, it goes far into the outer space. Okay. And this is one of the reason why we are having the shielding of our biomass from the harmful radiation coming in. Okay. So this is also a very important part why we are having the shielding. Okay. So this is because of the interior of Earth, and this is been given by the outer core. Okay. Outer core is responsible for generating the strong magnetic field in the Earth. Okay. And then another part which is important of this aspect is that if the question comes that, okay, fine, if we are having like the magnet, okay, so if you and any magnet, if you put at a very high temperature, okay, it will melt or it will demagnetize. But why again and again we are having like the strong magnetic field which keep continuing, okay, which is not destroyed completely. So the scientists they talked about this, and they have discussed, and what they found was that, for example, this I will just try to explain in this one, that the question is why is a magnet the field created by convection. Okay. This is because again it is the heat flow, and the heat flow keep on producing the convections. Okay. So now in laboratory, if you take laboratory experiments demonstrate that the field of permanent magnet is destroyed at around 500 degrees centigrade. Okay. And the interior of Earth, if you look, okay, we have the temperatures are very high. Okay. If you move beyond, because it may be more than 1000 degree or so. So the interior of Earth, or what the part is the outer core, is having very high temperature, and even though it is capable of holding this property, or it is of the magnet. Okay. So what it was suggested that we know that the temperature in Earth in the deep interior are much higher than that. Okay. And then thousands of degrees in the center. Okay. It is very high. So unless and until the magnet is not constantly generated, it will not it cannot maintain the magnetic field of the Earth. Okay. So it needs to keep on generating the magnet again and again. So this is one of the reason for generating, and of course it has been suggested that the convection currents which have been developed in the if you compare, because we have a partially molten layer, that is an asthenosphere, which is also partially molten. So why the magnet is not been generated there? Okay, why only in the core? The reason which has been given is that we have the silicate rocks. Okay. In the upper part of the interior of Earth, whereas we are having the iron and nickel, which are like good conductor of electricity, which sits in the interior of Earth, that is in the core. Whereas in the asthenosphere, we don't have we have the silicate rocks, hence they are poor conductor of electricity, so they don't help in generating the magnetic field and all that. Okay. And then second reason which has been given is that this the liquid core, the convection currents are much higher. Okay. So the motion is very rapid as compared to what we see in asthenosphere. So these are some facts of very important to be understood for the why we call Earth as a geodynamo. Okay. And moving ahead, there is another important part before we get into the plate tectonics, is the isostasy. And this principle, it says that the principle of isostasy governs, okay, the rise or subsidence of the crust until the mass is buoyantly balanced. Okay. So whatever you have, you see below the surface, you may have lesser on the surface. That has to be equally balanced. Okay. So because of isostasy, all parts of lithosphere are floating in equilibrium. Okay. So if suppose you are having you erode something from the surface, then that will result into the uplift, and that is what we see a very good example in Himalayan region. Okay. So we keep on eroding, the Himalaya keep on rising. Okay. Now the other point is that the low density, for example, there is an example given is the low density wood blocks, okay, float high and have deep root, okay, whereas the high density blocks float low and have shallow roots. Okay. And this is what has been explained, is that this one is the low density blocks, okay, float higher and have deep roots, whereas the lighter ones will have you can have the higher density blocks float low and have shallow roots, okay. So they will be shallowly. So similarly, this is another example which has been given, okay, as compared to the iceberg which has been there and the major mountain ranges, okay. So major mountain ranges about 60% above the average continent it remains, okay. Now similarly, what we see here, if we take in terms of the oceanic crust or the continental crust, the oceanic crusts are heavier and not so deeply rooted, but the continental crust which are comparatively, okay. So continental crust is less denser than the oceanic crust, okay. Therefore they rise higher, okay, as compared to that, okay. So continental floats high because they are made up of rocks with lower densities, okay. So they float higher as compared to the oceanic crust. So this is one of the reason and why we see that Himalayas are very high and the alpine Himalayan chain of mountains are sitting very high in terms of their height. Now coming to the main topic, what we were talking about, the plate tectonics. So whatever, like if we have the disturbance here, we will keep on having the rise every time. So plate tectonics, the three most important cycles, if we look at, okay, they are interlinked, okay. We say that the one is the hydrological cycle, and this is also again we can say that this is interlinked with the plate tectonics, because if the plate movements are there and if plate moves from one place to another place, the climatic cycle and everything will change, okay. For example, earlier we never had like for example Indian subcontinent, we never had Himalayas, okay. So we never had the monsoon, but now we have the monsoons. We never had rivers, but now we have the rivers and all that, okay. And that is reason is for is given that this is because of the plate tectonic movements or plate movements which resulted into the formation of Himalayas, okay. And then we have the rock cycle which is also interlinked, okay. So rock is formed, again this moment is based that the rocks are formed, modified, decomposed and reformed by the internal and external processes, okay. So here both the processes are involved, whereas this is in plate tectonic and external is the erosion and solidification or weathering, we can talk about that, okay. Then we are having tectonic cycles, okay. So movement of plates of lithosphere and their internal processes of Earth's deep interior that drives the plate, okay. So this also has been involved in this cycles, okay. So these are three cycles which are interlinked in a sense, okay, because they don't have like they are interlinked in a broader sense, okay. So rock cycle, if we take or if we and we look at the what it usually is composed of, the rock is an naturally formed non-living firm and coherent aggregate of minerals that matters that constitute the part of the plates, okay, planets. So we are having three types of rocks, as yesterday I was mentioning about this. We have igneous rocks which are created through the cooling and solidification of magma. So this is again very much related to the plate tectonics, okay, because not all places you will find that the magma is coming up on the surface or there is a volcanic eruptions, okay, because the source is through volcanic eruptions, particularly the magma coming up on the surface, okay. And so plate tectonic is an extremely important, it plays an important role when we are talking about the generation of magma. So the igneous rocks will form through the cooling and solidification of magma. Then we are having the sedimentary rocks. So when this material is coming up, the erosion will result into the formation of or the sediments, and then different sedimentary rocks are formed in different environments, okay. Then talking about the metamorphic rocks, which are formed mainly because of the effect of the pressure, high temperature and pressure, okay. So this again, when they are buried in the deeper part of the earth, they will be subjected to metamorphism, okay. So one rock will be transformed to another type of rock, okay. So for example, sedimentary rocks, if we take sandstone, will get transferred into the quartzites and all that, okay. So that is what there. And then if we are having the granite, maybe it will get transferred into the gneiss and all that. So we have that sort of a transformation from one rock to another rock when it goes under the process of metamorphism. So, this is the cycle which talks about that how they are interlinked. So, we are having like the continental crust. If we start from here, okay, or maybe you can say that we can start from this place. So, we are having geothermal energy. So, we are having the magma is getting heated up, okay, and then the rocks are melted and they are brought up to the surface, okay, through intrusion or volcanic eruption. So, the magma which is molten magma, it will be intruded in the country rocks, or it will be extruded on the surface through volcanic eruptions. So, that will result into the formation of the igneous rocks, and then those rocks are tectonically uplifted. So, ongoing deformation will result into the uplift and result into the formation of mountains and all that, okay, we are having. And here what we have that there will be a weathering process, because these sediments will be exposed to the solar radiation, or maybe you can say that the rain or through snow or any mean of the different type of agents, and they will be weathered and result into the formation of regolith or the soil, and then this process of weathering and will what we see the erosion and deposition of the sediments, okay, and upon burial and solidification or cementation, they will result into the formation of sedimentary rocks, and again they are metamorphosed at the deeper, folded, deformed, result into the formation or causing formation of metamorphic rocks. So, we have this cycle which goes on, okay, and so they are interlinked. So, the formation of rocks, destruction of rocks, and regeneration of rocks or reformation of rocks is completely linked with the plate motions, okay, or the plate tectonics, okay. We will learn that part in shortly, or how the rocks have been churned. So, rocks we have that what we discussed, okay. The rock cycle describes all processes by which the rock is formed, transported, decomposed and reformed, okay. So, decomposed means they are eroded and then deposited, okay, and then reformed, okay. Active volcanoes produce igneous rocks, mountain ranges rises as a result of plate tectonics. So, what we see, the mountain ranges have been resulted from the plate motions and deformation of the crust, okay. And then weathering and erosion changes the surface of the solid earth, okay. So, the erosion will result into the formation of the sediments, and then further sedimentary rocks, and then deep burial will result into the metamorphic rocks, okay. So, sediments is buried and compacted, eventually become the sedimentary rocks, and the deeper burial turns the sedimentary rocks into the metamorphic rocks, okay. So, even deeper burial may cause some metamorphic rocks to melt again and result into the formation of magma. So, this cycle keeps on going, and this never ends, okay. So, tectonic cycle, tectonic again is a word which has been used to for the branch which studies the movement and deformation of lithosphere mainly, okay. And then we talk with when the magma rises from the deeper part from the mantle, it forms new crust, okay. So, it keeps on, and some places it keeps on adding and the result into the formation of new crust, okay. And mainly this has been formed at the area where we talk about or we say the mid oceanic ridges, where we have the new formation of crust every time, okay. So, this is how it has been shown that how things are been interlinked, okay. So, this all cycles are interlinked, that is the hydrological cycle, rock cycle and tectonic cycles, they are interlinked with each other. Now, before we move to the part which we are talking about that and the plate tectonics and all that, okay. This in the last lecture we talked about that the geological time scale, okay. We have era, we have period, and then we have the epoch, okay. We are having this one, and right now what we are looking at, we are in the Holocene epoch, okay. And the most recent one, the period in geological time scale, if we have to take, okay, is the quaternary, okay. So, this is the most recent period we are having, okay. And then further they are divided into two, where we have the Pleistocene and we are having the Holocene epoch. So, let us see what we look at this. I have already discussed, so just I will move ahead, okay, and then talk. This is the time the person, okay, who introduced or gave the theory and tried to explain that the plates or the continents which we see today were not at the same place in the past, okay, but they were together long back, okay, but they moved from one place to another, and then and that is what he said about the continental drift, okay. So, they drifted from one place to another, and due to the convection currents which are generated within the Asthenosphere. So, he said that Earth has looked at the Earth as a jigsaw puzzle, okay. So, in 1912, okay, Alfred Wegener, a German meteorologist, okay, proposed that the continents were all together like one piece, okay, and that was been named as one land or all land, that is Pangaea. Then they drifted apart and reached their present locations, and that theory was been termed as the continental drift theory. So, this was been given by Alfred Wegener. Initially, not many people believed him, but now we can even measure the movement of the continents at millimeter accuracy by differential GPS. Okay. So, this is what he called as that Earth as a jigsaw puzzle. So, if you look at the boundaries of the African west side and the South American plate, okay, on the eastern part, okay, they matches or they fit each other very much, okay. So, this is like in puzzle which he talked about, okay. So, earlier what he suggested that in Pangaea, all continents, okay, were together, okay. So, if you match the boundaries of each continents, they will almost fit very much with each other, and that is what he termed as in Pangaea. This was the long back, okay. So, now if you look at the landmass, which the theory which has been given, okay, that we had all the continents were together, and it was been engulfed by ocean which was been termed as Tethys Sea, okay. And here it is the India. This is your Indian subcontinent, which was almost like thousands of kilometers south of equator, which located, and it moved towards north, okay, and then finally it collided with the Eurasian plate, okay. This is Eurasian plate here having. So, this is what has been termed as, and then the northern side, the continents on the northern side of the equator were been termed as Laurasia, and the continents which were on the southern side were termed as the Gondwana land, okay. And India lied very much south of the equator, okay. But now if we look at it, is almost, it has traveled lot many kilometers to reach its present position. Now, that was not what they studied was that they tried to look at, okay, and then the geologists or the paleontologists they tried to look at that, okay, fine, if these continents were together, then they must have almost similar climate, okay. Hence, the floras and faunas should be almost similar, okay. So, that what they tried to look at, and they found, okay, fine, that there were the areas which showed that the floras and faunas were very much similar in the subcontinents, okay. And then another one, what they looked at, that, okay, fine, these regions might have experienced in particular climate, okay. So, anyways, I will continue in the next lecture. Thank you very much.